Alright, ladies and gents, these are the topics we're going to cover on this redox review video: oxidation states, oxidation reduction, half reactions, how to use table J, and last but not least, balancing redox equations. Alright, we're going to start with oxidation states and how you assign them based on some of these rules. And here, for compounds and free elements, they share something in common. So for the compounds, some of the elements, of all of the elements, and then for the free elements, they're all equal to 0. So the charge on a free element is 0, for example. You have O2, H2, etc. So if you have an element that's by itself, regardless of the subscript, it's 0. For compounds, for example, NaCl, NH3, if you don't see a charge right there, then it's a compound, and the sum of all the elements, their charges is equal to 0. Now for ions. The charge is whatever's given. So given charge. An example of that would be OH minus, H plus, Na plus, something like that, or SO4 2 minus, that's a polyatomic ion, for example. Hydrogen, a lot of the elements, you could easily pick them off the periodic table if you look for the oxidation states, but certain elements like hydrogen and oxygen come with certain rules. And then you're going to see some other elements with multiple oxidation states. So my strategy for you guys is to first establish what's already for sure, like oxygen is most often 2 minus, -2, except when it's in a peroxide. And then it's just a -1. So when oxygen is bonded like in a peroxide, then it's a -1. Peroxide, hydrogen peroxide as an example, is H2O2. So in that example, each oxygen there will carry a charge of -1. Now going back to hydrogen here. Hydrogen is often +1, except when bonded with metals, then it's -1. For example, would be NaH. And there, hydrogen would be a -1, Na will always be +1. Alright, now don't be alarmed by this phrase and the drawing right there. That's my little doodle of a lion. And so here's my phrase for remembering redox. Leo the lion says grr. What does that mean? Helps us differentiate between oxidation and reduction. So Leo stands for losing electrons, oxidation. So in oxidation, you're losing electrons. Whereas in reduction, Leo the lion says grr, gaining electrons, reduction. Gaining electrons is reduction. Alright, here's some key facts about them. Oxidation, when you're losing electrons, so the charge becomes more positive. In reduction, charge becomes more negative. And that's because electrons have a negative charge, so it sounds a little counterintuitive to think that you're reducing something and you think it might lose electrons, but actually when you're reducing something, you're gaining electrons, and therefore you're actually reducing the charge to a negative value. That might be an easy way to remember. Now, let's see here. When you're being oxidized, so the substance being oxidized, you're also known as the reducing agent. So by you losing electrons, you're helping something else gain electrons. So the oxidized substance also doubles as the reducing agent. Likewise, for reduction, the substance being reduced is the oxidizing agent. So by you gaining electrons, you're helping, as an agent, something else being oxidized. You're helping something else lose their electrons by you gaining. Alright, now here are some examples. Let's do in purple. As an example of this, let's say zinc starts at a 0. Now becomes zinc 2+. Therefore, it lost 2 electrons. Notice how here you start with a 0 charge and it becomes more positive when you lose electrons. So the electrons are always located on the right side, on the product side, as if you're releasing electrons, so you're losing them. On the other hand, if you're going to show a reduction, you're going to reverse this. So by reversing this, you have zinc going from positive to more negative, so it starts to go to 0 closer to the negative side, and it looks like here the electrons are on the reactant side, so it looks like that zinc is absorbing those electrons to become more negative. So when you're looking at a redox reaction, that means both oxidation and reduction happening at once, you're going to split it up into half reactions. So it helps you be able to identify which one's being oxidized and which one's being reduced. So we're going to start with this example of 2H2 plus O2 yielding 2H2O. We take each of these substances, H2. First you need to identify what is their charges to begin with. And look here, each of these, H2 and O2, they stand by themselves as free elements. So let's start with this one. H2 is a free element, so it starts out at 0. And then we look on the other side, becomes H2O. So we identify their oxidation states before we even decide what's happening. So H2O, O will be a -2 here, 2 minus, and then here will be a +1. In order to balance out the 2 minus, each of these H's have to be +1 to make sure everything balances out to 0. So here we have 2H2 going into 4H+. And in order to go from 0 to plus, each of these H's have to lose 1 electron, and because we have 4 of them, we have to put 4 electrons on the other side. Now the other reaction here is with oxygen. O2, it starts out as 0, and it becomes 2O2 minus. So now this means that each of these oxygens have to gain 2 electrons. And so because we have 2 oxygens, so it's 4 electrons being gained total. Oops. All right. That means we put the electrons on the other side to show that it's gaining electrons. Now this right here, I'm going to bracket this off. Because we see a loss of electrons over here, this is now oxidation. On the other side, we see a gaining of electrons here. So this makes it reduction. So here, hydrogen is the oxidized substance, while oxygen is the reduced substance. In terms of the agents, it's the opposite. This is now the reducing agent, while oxygen is the oxidizing agent. There we go. So this is the purpose of using half reactions, so that we are able to identify the oxidation and reduction reactions as well as who are the agents in this reaction. Alright, table J is pretty fun. It's pretty simple as well. So it helps us identify which are spontaneous and non-spontaneous reactions. So in spontaneous reactions, we're having a free element replacing another element in a reaction. So they often deal with single replacement reactions. So the free element you're looking at has to be, whoa, sorry, this is a typo. There's a typo right here. Oh my god, this is supposed to say more. So the free element has to be more active than the element it's replacing. So I'm going to have in another standing element. So let's say we have, chromium. plus cobalt time combining with element X. X stands for whatever. And then here, chromium is gonna replace cobalt. So we get CrX plus cobalt. So let's identify here. Chromium and cobalt. We look at the table right here. Chromium and cobalt. Since chromium is more active, that means it's above cobalt. Therefore, this is spontaneous. On the other hand, if we had the reverse, so let's say we had lead by itself plus zinc Y. Y is just whatever made up. And then becomes PbY plus zinc. So here, lead is replacing zinc. We identify it on the table. There's lead and there's zinc. Because zinc is over lead, lead is less active than the element it's replacing, which is zinc. Therefore, this is non-spontaneous. So you got to use table J to help you figure this out. And on the other side of this table is the same thing. These are nonmetals, and the other side is metals. Alright, now this is where that worksheet I gave out today in class, guys. We're going to use the half reaction method in order to balance redox equations. And the purpose of this is to show conservation of charge and mass. So the first example. Here, we have to use the half reaction method. That means we split this up into two half reactions. So we have Sn going over to, starting with a charge of 0 and going over to a charge of plus 2. That means it lost electrons, 2 electrons for this reaction. And now this other one, silver, has to gain an electron because it goes from plus to 0. Now in order to balance this out, we see here there's a discrepancy of charges. There has to be an equal number of charges being exchanged. 2 electrons, and we have 1 electron here. So we gotta find the least common multiple. The quickest way is to multiply by the coefficient of the charges. So here we cross multiply. So we take this 2, multiply in front of here, take the 1 over here, and multiply it over here. And we distribute it. So that means our new coefficients are then going to be, we keep the 1 here, put a 2 in front of here, put a 1 here, and a 2 in front of here. You don't have to put the 1s are understood. And now we definitely have a conservation of both charge and mass. Now I highly suggest you pause the video right here so you could try this second example for yourself. But I'm going to keep going. So we start with chromium, sorry, I keep saying chromate. Goes to Cr plus 3. And then we have lead gaining electrons to become Pb0. We look at our electrons, because they're different, we could just cross multiply. Put a 3 here. Put a 2 here. So we put a 2's in front of the 2 chromates, and 3's in front of the leads. And that's it. We've reached the end of this redox review video. I apologize for the sickly state of my voice and of my nasal cavities. I have probably sneezed and coughed a bajillion times throughout the making of this video, but you guys didn't hear that.